For introduction, there is two categories, which is second order linear homogeneous versus second order linear non-homogeneous. A linear and order differential equation of the form is equal to 0 is said to be homogeneous, whereas an equation is equal to gx. With gx not identically 0 is said to be non-homogeneous. For example,
Now, I would like to explain a real-world example of second-order linear homogeneous differential equation, the small angle oscillation of a simple pendulum. Pendulums are commonly used in clocks, seismographs, and playground swings. A simple pendulum consists of a mass suspended by a string of fixed length. When air resistance is negligible and the angular displacement is small, its motion can be modeled by a second-order linear homogeneous differential equation. To model this motion mathematically, we apply Newton's second law in the tangential direction. The restoring force acting on the pendulum is mg sine theta. By equating this force to the mass times the tangential acceleration and we simplify the equation, we obtain the equation of motion. Since we are considering small oscillations, we use the small angle approximation sine theta approximately equal to theta. This simplifies the model to the second order linear homogeneous differential equation, which is shown in the slide. To solve it, we assume a standard exponential solution form, which is theta equals to e to the power of rt, taking the first and second derivatives and substituting them back into our equation, give us a characteristic equation, which is r squared plus g over l equals to 0. Solving for r, we find that the roots are purely imaginary complex number, which is r equals to 0 plus or minus the square root of g over l times I. Using our complex roots where alpha equals to 0 and beta equals to square root of g over l, we find the general solution for the angular position over time. It simplifies perfectly to a combination of cosines and sines. Physically, this represents continuous simple harmonic motion. For this solution, we can easily pull out the angular frequency and the exact period of the pendulum.
So for the sample question for concept number 1, a pendulum consisting of a small metal bob is suspended from a light string of length 2.5 meter. The pendulum is displaced by 8 degrees from its equilibrium position and released from rest. Since the angular displacement is small, which is smaller than 10 degrees, the motion can be modeled using the small angle approximation. So first step, we form the differential equation governing the motion of the pendulum. And then finally, we get the second derivative of theta plus with 3.924 theta equal to 0. We assume it as equation number 1. So in step 2, we determine the general solution for theta t. So firstly, we differentiate twice theta is equal to e to the power of rt, and then we substitute equation 2 and 4 into equation number 1. And then since we know that e to the power of rt is not equal to 0, and then finally that we found that r is equal to a complex number. By comparing the general form of the complex root, so we get alpha equal to 0, beta is equal to square root of 3.924. And then the general solution is shown as equation 5. And then by substituting the value of alpha and beta into equation 5, and then we get our equation 6 as our general solution. In step 3, we use the initial angular displacement of 8 degrees to find the radian. After finding the radian, and then we know that theta 0 is equal to 0.1396, and then we found that C1 is also equal to 0.1396. After that, we differentiate it because we know that the derivative form of theta is equal to 0. So finally, we get C2 is equal to 0. So we substitute these two answers, C1 and C2, into our equation 6, and then we finally get our particular solution. Finally, we calculated the angular displacement after 2 seconds and determined the period of oscillation. The angular displacement after 2 seconds is approximately negative 0.0952 radian, while the period of oscillation is about 3.17 seconds.
Okay, so now we go on to the scenario 2, which is SC-RLC circuit. This is such a real-life example for the second-order linear non-homogeneous differential equation. So, an RLC circuit consists of a resistor, an inductor, and a capacitor connected to an alternating voltage source. The charge and the current in the circuit vary with time due to the combined effect of resistance, inductance, capacitance, and the external voltage source. So the usage of a RLC circuit is for the radio receiver, the television system, communication device, and the power electronics. So now we go to the equation part. First, the AC source supplies a sinusoidal voltage given by the equation ET is equal to V0 sine omega t. So according to the Kirchhoff's voltage law, the sum of the voltage drop across the component must equal to the applied source voltage. So it will get the second equation, VR plus VL plus VC is equal to ET. So we substitute the equation 1 into the equation 2, and the component is VR is equal to RI, VL is equal to L di dt, and the VC is equal to Q over C. And then we will get the new equation, Ri plus L di dt plus 1 over CQ is equal to V0 sine omega t. since the current is the rate of change of the charge, so I is equal to dq over dt. So we can get a new equation, r dq dt plus l d square q dt square plus 1 over cq is equal to v naught sine omega t. So by rearrange, we can get the equation L d square q over dt square plus r dq dt plus 1 over cq is equal to v naught sine omega t. So right now we can get a non-homogeneous differential equation. So let's move to the next part. So for solving the differential equation, step 1 is the general equation. So we consider the homogeneous equation L d square q dt square plus r dq dt plus 1 over cq is equal to 0. So we assume that q is equal to e power of rt, dq dt is equal to r e power of rt, and d square q dt square is equal to r square e power of rt. So by substitute this equation into the homogeneous equation, we can get L r square e power of rt plus capital R e power of rt plus 1 over c e power of rt is equal to 0. So we can simplify, we can get e power of rt in the bracket L r square plus capital R plus 1 over c is equal to 0. Since that e power of rt is not equal to 0, so we just consider the part behind, which is L r square plus capital R plus 1 over c is equal to 0. So by using the formula, x is equal to negative b plus minus square root b square minus 4ac over 2a. And the roots we'll get are r is equal to negative capital R plus minus square root capital R square minus 4l over c, and overall over by 2l. So we can, after we factorize, we can get r1 is equal to negative r plus square root r square minus 4l over c over 2l. And r2 is equal to negative r minus r square minus 4l over c over by 2l. So thus we can guess QC is equal to C1 e power of R1t plus C2 power of E2. Step 2 is for the particular solution. So we already get V naught sine omega t. So we assume that QP is equal to A cos omega t plus B sine omega t. After we do the first derivative and second derivative, we can get these two equations. And we substitute all these equations into the equation 3, we can get L in bracket negative A omega square cos omega t minus B omega square sine omega t plus R in bracket negative A omega sine omega t plus omega cos omega t plus 1 over C A cos omega t plus B sine omega t is equal to V naught sine omega t. After we calculate, we can get this equation L negative L A omega square plus R B omega plus C A cos omega t plus negative LB omega square minus RA omega plus CB sine omega t is equal to V naught sine omega t. By comparing the coefficient, we can get cos omega t is negative LA omega square plus RB omega plus CA is equal to 0. Sine omega t is equal to negative LB omega square minus RA omega plus CB is equal to V naught. By solving simultaneous equation, we can get the value of A and B. Hence, the particular solution is QP is equal to A cos omega t plus B sine omega t. So we complete the solution, we can get QT is equal to QC plus QP, or QT is equal to C1 e power of R1t plus C2 power e power of R2t plus A cos omega t plus B sine omega t.
Okay, so next I will present the questions for the second order linear non-homogeneous differential equations. So the question is that find the charge on the capacitor in an LRC series circuit at time equal to 0.01 second. And then the question is given some condition. Then we need to determine the first time in which the charge on the capacitor is equal to 0. Okay, so the step 1 is form the differential equations. So by using Kirchhoff's voltage law, L times d square q over dt square plus R dq over dt plus 1 over cq equal to ET. So next we substitute the value from the equations to our equation, and then we multiply all the equation by 20. Okay, so step 2 is find the complementary solutions. So we assume q equal to e power to rt, and then dq over dt equal to r times e power to rt, and then d square q over dt square is equal to r square times e power to rt. So next, we substitute the equation 4, 5, 6 into our equation 3. So since e power to rt not equal to 0, so the r square plus 40r plus 2000 is equal to 0. And then the step 3 is solve the characteristic equations. So by using the formula x equal to negative b plus minus square root b square minus 4ac over 2a, so we solve the quadratic formula. And then we will get the complex root, that is r equal to a plus minus bi. So by comparing, so we know that A equal to negative 20 and beta will equal to 40. Okay, so the next step is form a general solution. So since our roots are complex, so we know that Qx is equal to e power to negative 20t times to c1 cos 40t plus c2 sin 40t. Okay, after that, we apply initial condition Q0 equal to 5. So substitute when t equal to 0, so we know that c1 will equal to 5. Okay, so the step 6 is differentiate our general solution. After we differentiate the general solution, so we must simplify all the equations. So we will get the Q prime will equal to e power to negative 20t times the negative 100 plus 40c2 times cos 40t plus negative 20c1 minus 200 sin 40t. So step 7 is apply I0 equal to Q prime 0 equal to 0. So now we substitute t equal to 0, so we will get that C2 will equal to 2.5. So step 8 is we find the particular solutions. So we're substituting C1 and C2, so we will get Qt equal to e power to negative 20 times 5 cos 40t plus 2.5 sin 40t. So this is the particular solution of these equations. Okay, next we can find our charge when the time equal to 0.01 by using our particular solutions. So which is the charge is 4.57. And then the last step is find the first time when Qt equal to 0. So by using our particular solution equal to 0, so since e power to negative 20t will never equal to 0, so we know that 5 cos 40t plus 2.5 sin 40t will equal to 0. So we solve our equation, so we will get t is approximate to 0.0509 seconds.